All right, so this class is on Lewis diagrams, okay? And this is mostly review of previous grades on how to draw certain Lewis diagrams. The only new thing that we're going to learn today is formal charge. Okay, so let's start the review first. So first of all, we learned that valence electrons can be determined using electron configuration. That was the lesson yesterday. So the best way to determine valence electron is therefore using electron configuration because that's the most accurate model. Now, the problem is that takes too long. You have to write out the configuration first. So with Lewis diagrams, you have to determine valence electrons of certain atoms fairly quickly because you're going to need to add them up and draw your diagram. So using electron configuration is just very inconvenient. So instead, there's a shortcut. And in this picture, you can see that shortcut. Just like you learned this in grade 10, the alkali metals, group 1, you have 1 valence electron, and there's no exception there. Group 2, the alkaline earth metals, you have 2 valence electrons. We're going to skip all the transition metals because we're not going to see a question with the transition metal. So if you go to group 13, starting with boron, everybody in that column would have 3 valence electrons, and then the next one will have 4, and then the next one's 5, and then 6. All the halogens in group 17, they have 7 valence electrons, and noble gases, they have 0. So this is a really quick way of determining who has what valence electron. All right, and you need to be able to do this fairly quickly to save some time. So I suggest you memorize this thing. If not, you can just whip out your periodic table, find your element, and depends on which column it's in, you can just deduce the amount of valence electrons. So to draw Lewis structures, we're going to start easy. All right, so this is just drawing individual atoms or ions. So just one thing, no bonds at all. And there are many rules with regards to drawing Lewis structures, and you need to know these rules in order to get the structure correct. So for the most simple atom, the first thing you do is you have to determine the number of valence electrons. All right, and if you have an ion, that means you've gained or lost electrons, you have to account for that as well. If you gain electrons, you just add more electrons. If you lost them, you subtract. So once you determine the number of valence electrons, you write the chemical symbol of the atom in the center. And then you fill the atom with the valence electrons. And you do this clockwise. Now, if you prefer counterclockwise, that's also okay. But you have to go in a circle. You can't just randomly start plotting points. And what I recommend is you start at the top at 12 o'clock, and then the next one you draw this at 3 o'clock, and then the next one 6 o'clock, and then 9 o'clock, and then you go in a circle like that. So you pair electrons only if you have to. All right, electrons don't like to be paired up because they're all negative. They want to be as far apart from each other as possible. So for the first 4, you separate them in the 4 corners. And then if you have more, then you have to pair them up. Okay, so don't pair for no reason. And then lastly, if you have an ion, you need to place square brackets around your structure, and you put the charge of that ion on the top right corner. So let's do some examples of just individual atoms or ions. Okay, so these are supposed to be very simple. The first one being aluminum. So the chemical symbol of aluminum is Al, and you can see from the periodic table, aluminum has 3 valence electrons. So all you have to do is go 1, 2, 3. You start from the top, you go clockwise, and 12 o'clock, 3 o'clock, and 6 o'clock. So there is your aluminum atom. That's it. That's all you have to do. For sodium ion, this one is even easier. Sodium has 1 valence electron, but since this is the sodium ion, that means you would have lost that electron, so you have no valence electrons. So just write Na, and because this is an ion, square brackets and the plus charge. All right, so you don't have a valence electron, and this is what your structure will look like. For C, you would have nitrogen, as simple as N. Nitrogen has 5 valence electrons, so you start from the top and you go around in a circle. So you go 1, 2, 3, 4. All right, so you need one more. So then you have to pair them, and you will pair the one on top. That's the convention. Now, if you want to pair the one on the side, doesn't matter. So if you do that, you have nitrogen. And it is important to note that nitrogen has exactly one pair and 3 single electrons. All right, nitrogen has one pair, and that pair is called a lone pair. Why is it called a lone pair? Because it doesn't make a chemical bond. It is alone. Whereas the 3 other electrons that are single is going to try to find another electron to bond with. So those are bonding electrons. The last example is the sulfide ion. Okay, a sulfide ion would have a -2 charge because sulfide needs 2 extra electrons. So in this case, this ion will have 8 valence electrons. The whole point of gaining electrons is to make 8. So you start from the top, you go 1, 2, 3, 4, that's the first 4, and then you start to pair them up, 5, 6, 7, 8. All right, so that is the 8 valence electrons, and then finally you need to put square brackets around them because it's an ion, so 2 minus. All right, so that's how you would draw individual atoms and individual ions. Okay, so does that make sense for everybody? All right, good. So knowing this, we can finally do compounds. So you can have ionic compounds and molecular compounds. We're going to study ionic compounds first. Those are easier to draw than molecular compounds. So to draw ionic compounds, all you have to do is draw the ions for all the ions that you have. And then all you have to do is put them together. So situate them adjacent to each other. And the last thing you want to make sure is all the positive ions are separated by the negative ions. So you cannot have 2 positives and 2 negatives sitting next to each other. And those are basically the only rules for ionic compounds. So I'm going to show you the first 2, A and B, and I'll have you do C and D. Okay? So for the first one, sodium chloride. You have to recognize that this is an ionic compound because you have a metal and a non-metal. So sodium chloride is ionic. You draw the 2 ions. You draw the sodium ion, and then you have to draw the chloride ion. And that's what they will look like. The sodium ion we've already done before. Sodium Na. It lost its electron, so you don't have any valence electrons. So square brackets plus. Chlorine has 7, but then gaining 1 to make the chloride ion, you would now have 8. So you draw 8. And because you're 1 minus, you put a square bracket 1 minus. And notice that I made them really close to each other because in an ionic bond, the plus and the minus, they attract, so they should be close to each other. And this is the Lewis structure for sodium chloride. Okay. Potassium oxide is the next one. Well, for that one, you have to first of all figure out the chemical formula. Potassium oxide, you have to know that this is K2O. And because potassium has a charge of +1, oxygen has -2. And if you want to balance the ionic charges, you have to have 2 potassiums for 1 oxygen because 2 1 pluses equals to 1 2 minus. So knowing this, you need 1 oxygen and 2 potassiums. And as a result, you put the oxygen in the middle because you only need 1 of them, and you surround the oxygen with 2 potassium ions. All right, and potassium ions are exactly like sodium ions, except it's not Na, it's K. It doesn't have a valence electron because it lost it. Oxygen would have 8 valence electrons because you gain 2 additional ones to become oxide. So this would be potassium oxide. All right, make sure that the oxygen, the negative, separates the 2 positives, and they're really close to each other. All right, so all the other ionic compounds work the same way. So I'll give you like 2 minutes to work on C and D, and then I'll take it up very shortly. So I'll give you 2 minutes starting now. Okay, so I'm going to take up the 2 examples here. For C, you have calcium sulfide, and the formula would be CaS. Because calcium is 2+ and sulfide is 2-, so it's a 1-to-1 ratio. You just need 1 of each. And so for calcium, notice that positive ions are really easy to draw. You probably lost all your valence electrons, so you have nothing. So Ca with the 2 plus. And the sulfide, because you gained 2 electrons, you have a full octet. So that's 8 valence electrons with -2. Okay, so make sure you have the brackets and the charge. So that is CaS. That's all you got to do. Now, the next one, magnesium fluoride, is a little bit more complicated because Mg is a 2 plus, fluoride is a 1 minus. So that means you need 2 of those. The formula is MgF2. Okay, whenever you have an imbalance, whoever is fewer goes in the middle. Because you want to use the positive charge to separate the 2 negative charges. You can't have the 2 fluorides beside each other. So magnesium must be in the middle. So you will then surround that magnesium with the 2 fluoride ions, which are identical to chlorides. Just change Cl to F. 8 valence electrons with a minus charge. Magnesium they have no valence electrons with a +2 charge. All right, so, and that's all you got to do. For ionic compounds, all you got to do is just draw the ions, put them together, and just make sure that no 2 same charge are together. Okay, do we have any questions regarding ionic compounds? Okay, so ionic compounds are supposed to be easy to draw, and typically students don't have any issues with that. The only mistake that I noticed is because we're going to learn molecular structures next, and we're going to spend a lot more time on those because they're way harder. So students, after having practiced a lot, they got the hang of molecular structures, and then on the test they see an ionic one, they will do the molecular way because they've been doing so many molecular structures, they just assume everything's not molecular. So that would then be wrong. Okay, with ionic compounds, you don't have a line to represent a bond because a line represents the sharing of electrons, and that would be a covalent bond. For ionic compounds, you don't have lines, you simply put the ions next to each other. So make sure on the test, if you have an ionic compound, you draw this in the ionic way. All right, so that's the only issue that I've noticed. So let's move forward with formal charge. This is something new that you had to learn. The reason that we're learning formal charge is because formal charge can be a very useful tool to check whether your answer is correct. First of all, the definition of a formal charge, basically that is the charge of an atom or a molecule, atom in a molecule. Now you assume that all of the bonds are shared equally, regardless of the electronegativities. Okay. Now see, the definition doesn't really matter. If you don't understand or don't remember the definition, that's fine. All you need to do is know how to calculate the formal charge, and you calculate it, and then you have to interpret the numbers that you get from the formal charge and decide whether the structure that you drew was correct. Okay, it is a checking mechanism. So you need to know how to find the formal charge. So that formula right there, Fc, the formal charge, is the valence electrons, subtract the non-bonding electrons, subtract the number of bonds. So look at that water molecule right there. What do I mean by a non-bonding electron? I circled 2 of those. So those electrons are not in a bond, so they're non-bonding electrons. So in this case, oxygen has 4 non-bonding electrons because it's got 4 dots. The number of bonds, a line is a bond. So that oxygen-hydrogen bond is an example of a bond. And in this case, you have 2 bonds, all right? And the valence electron, well, that would be the valence electron of the atom that you're looking at. And you can find this on the periodic table. Right? Oxygen is always 6. Hydrogen is always 1, for example. All right, so we're going to do some examples with formal charge. Hold on, let me just let that student. So here are 2 examples. I gave you 2 Lewis structures, and it says determine the formal charges of each element in the following structures. I'll show you how to do these 2, and then for the next few, you can practice on your own. So on the left, you have carbon dioxide, and that would be the structure of carbon dioxide. Your job is to find the formal charges of the carbon and the two oxygens. So, for the carbon, you have to count the valence electrons of carbon, and it is always 4 because carbon is found in group 14. All carbons have 4 valence electrons, so that's 4. That specific carbon in the drawing, it has no non-bonding electrons. So every single electron of that carbon is in a bond, so you have 0 non-bonding electrons. And how many bonds is it making? It's making 4 bonds, 2 double bonds, 1 with each oxygen. So those are the numbers for the carbon. Okay, and you can do the same thing for the oxygen. Because those two oxygens are exactly identical, they both have 2 bonds, and they both have 4 electrons that are not in a bond, so they're the same. You just have to write this once. So oxygens all have 6 valence electrons. Those specific oxygens in the compound, well, they have 4 non-bonding electrons and 2 bonds. So you can apply the math. For carbon, it is 4 minus 0 minus 4. You get 0. And for oxygen, it is 6 minus 4 minus 2. And you get a 0. All right, so the answer to this question is, well, the formal charge of carbon and carbon dioxide is 0. And the formal charge of oxygen, well, both oxygens in carbon dioxide, they're 0. Okay? And if you move on to the question to the right, you have phosphorus pentachloride, PCl5. You have to find the formal charge of phosphorus and the formal charge of all the chlorides. So for phosphorus, you have 5 valence electrons. All phosphorus has 5 valence electrons. None of them are non-bonding. Okay, they all participate in a bond, so you have 0 non-bonding. 5 bonds were made, so that's the numbers that you have to write down. For chlorides, you have 5 of them, but they're all exactly identical, so you just have to do this once. 7 valence electrons for chlorines. They have 6 electrons non-bonding, and then finally you have 1 bond. So if you apply the math, for phosphorus, it's 5 minus 0 minus 5. So again, the formal charge of phosphorus is 0. For the chlorine, you have 7 minus 6 minus 1. Again, you get 0. So with this example, what can you tell me about the formal charges? What do you think they should be? Anyone?
They should always equal 0?
Exactly. For a compound, the formal charges of everybody should be 0. Okay? Now, this is not always true. For most compounds that are stable, the formal charges of everybody, they're all 0s. Now, there are exceptions. Sometimes you don't have all 0s, and that's fine, and those can also exist. It's just that the most preferred state is everyone having a formal charge of 0. You want 0s across the board. If you can't get that, the next best thing is to be as close to 0 as you possibly can get. So 1 and -1, they're acceptable. If you have a 2, then no, that is not acceptable. If you have a 2, then that means your molecule is very unstable. You need to change the structure. Does that make sense? So that's how we use formal charges. You want to check. If you get 0s across the board, you're probably right. Okay? And if you don't have 0s across the board, well, then you're probably wrong. And if you can help, if you can change anything, do it. Now, here are 2 more practice questions. Please determine the formal charges of every element in these 2 compounds. All right, so just do the math, and I'll take it up in 2 minutes. Okay, I'm going to pause and give you 2 minutes. All right, let's look at HCl first. HCl is quite simple. You just have 2 elements, so hydrogen and chlorine. If you look at the chlorine, all chlorines have 7 valence electrons, and this one in particular, well, it has 6 non-bonding electrons, so 6 dots around the chlorine, and 1 bond. And for the hydrogen, all hydrogens have 1 valence electron, and none of them are non-bonding, and you have 1 bond. So if you do the math, well, 7 minus 6 minus 1, that is 0. So the formal charge of chlorine is, again, 0. For hydrogen, it's 1 minus 0 minus 1, it's 0. By the way, the formal charge of hydrogen is always 0 if it's in a bond. Okay, so you can just omit that calculation in the future. If you see hydrogen bonded to anything, the formal charge of that hydrogen is going to be 0. Okay, so again, you have 0 across the board. This tells you that this structure of HCl is very accurate. This is a very stable molecule. Now, the one on the right is a lot more difficult. That's the nitrate ion, NO3 minus. So to do this, it's the same idea. Nitrogen has 5 valence electrons. That particular nitrogen in the compound has no non-bonding electron. They're all in a bond. And this one is making 4 bonds. So if you see 4 lines sticking out of the nitrogen. The oxygens, however, they're not the same. You see, there's the one with the double bond, and there are 2 with single bonds. So I'm going to have to distinguish between them. I'm going to use A to denote the double bond and B for the single. So for the one with the double bond, you have 6 valence electrons. 4 of them are non-bonding, and it made 2 bonds. Whereas for B, you have 6 valence electrons again. 6 of them are non-bonding, and there's 1 bond being made. So if you do the math, for nitrogen, it's 5 minus 0 minus 4, and that is positive 1. For the oxygen with the double bond, it is 6 minus 4 minus 2, that's a 0. And lastly, for oxygen with the single bond, 6 minus 6 minus 1, you have negative 1. So in this particular example, you don't have zeros across the board. So nitrogen has a +1 formal charge. The 2 oxygens that have a single bond, they have -1 formal charges. And that's okay. Okay, and by the way, all the formal charges in the compound, they should add up to equal to the net charge of the compound. So in this case, nitrogen has +1. You have -1 and -1 for 2 of the oxygens, so -2, and you add them up, you get -1, which matches the net charge of this nitrate molecule. All right, so in this case, you don't have all zeros, but they're pretty close to 0. 1 and -1 are really close to 0, so this is acceptable. So this is also a good structure. There's nothing you can do to make them all zeros, so you have to be content with this. All right, so do you have any questions? I'm sorry, say that again. There was a question? No?
Wait, I actually have a question.
Mm-hmm.
So do the formal charges have to add to 0? Like
only if your molecule is neutral.
Okay.
Now, for the nitrate, it's not neutral, it's -1, so they must add up to -1. And it does. You see what I mean?
If you have a like something like that has a charge, you need to add up with the same number.
What do you mean by that?
Like the formal charge.
Yeah, the formal charge of every single atom in your compound, they have to all add up to your overall net charge.
So in this case,
if you have like
-2.
phosphate 3-, then you have a formal charge, a sum of all the formal charge of -3.
Yeah. Okay. Thank you.
Okay, that makes sense, guys? So any question regarding how to calculate formal charge and what it is used for? All right, cool. So finally, with that knowledge, we can draw molecular structures, okay? You can see that, well, there are many rules for drawing molecular structures, so this is way more complicated. And in grade 10 and 11, we also learned how to do this. It's just we never taught you formal charges because you didn't need to know them. The structures that you learned in grade 10 and 11 are fairly easy to do, so you don't need to check the formal charges because there won't be any ambiguity. But for grade 12, you're going to get some really hard Lewis diagram questions, and you won't know whether you got the answer right or not if you don't check with formal charges. So that's why we learn it now. So let's go through the list. Here is a list of rules that you have to follow very strictly. Okay, now if you already know the structure of what you're going to draw, then okay, fine, skip all the rules, just draw them. But if you don't know how to draw something, if you follow these rules, you'll never get it wrong. You will 100% get it right. So what are the rules? First of all, you count the valence electrons of every single atom in your compound, and then you add them up. And if your compound has a charge, you have to account for that. You have to subtract electrons if it's plus, and you have to add more electrons if the charge is minus. Okay, so you have to add up the sum of all the valence electrons. And then you have to place one of the atoms in the middle and surround it with all the other atoms. Now, who goes in the middle? Well, the general rule is you pick the one with the lowest electronegativity. And again, we learned in grade 11 what electronegativity is. That simply means the tendency of an atom to attract electrons. So how good are you at attracting electrons? Okay, atoms come in different degrees of electronegativity. You take the lowest one, you put it in the middle. Now, this is just a rule of thumb. There are exceptions to this. And carbon always goes in the middle. Okay, hydrogen is never in the middle because hydrogen can only make one bond. How can you be in the middle if you can just make one bond, right? So hydrogen never in the middle. Carbon always in the middle because carbon can make 4 bonds. If you can make 4 bonds, that is a really good candidate to be in the middle because you can connect to 4 other atoms, all right? Another way of looking at this is the atom with the highest bonding capacity goes in the middle, okay? Whoever can make the greatest number of bonds, that's you. You go in the middle, okay? Now, if all else being equal and you don't know, you follow the rule with the lowest electronegativity. All right, so once you pick an atom to be in the middle, you have to connect it to all the other atoms using a dash. A dash represents a bond. Okay, that's the second step. After having done that, your molecule right now is naked. You don't have any electrons, you just have the bare structure. And you calculated how many total valence electrons you have, you start to add it to your structure. You give electrons so that you use up all your valence electrons and you satisfy all the octets. Okay, now who do you give the electrons to first? Because you're going to have multiple atoms and they all want electrons. Who gets them first? There's a hierarchy. There's a priority list. If we all get stranded on an island and a helicopter comes and drops food, who gets the food first? Well, obviously I do because I'm more important than you guys, right? There's a hierarchy. So same thing here. Who gets the electrons? The ones that get the electrons first are the most electronegative atoms, okay, because they're the most desperate for electrons. The definition of electronegativity, they're really good at taking electrons. So they're going to call dibs and they get the electrons first. And then whatever is left over, you give it to the weaker ones. All right, you give electron to the center atom last because by definition that has the lowest electronegativity. All right, so moving on, you must satisfy all the octets, obviously 2 or 8. And if the central atom doesn't have an octet, so you ran out of electrons to give to the central atom. Okay, too bad, the leftovers just doesn't cut it. Well, then you have to form double bonds with the central atom until the central atom has a full octet. Okay, you can't just leave the central atom starving. You gotta provide extra electrons by giving it double bonds or triple bonds if that's necessary. After having done all of that, everybody has 8. All the atoms are connected with each other, and you're happy. Check the formal charges to see whether it is the most favorable structure, because there are many ways of connecting atoms, and you might not have the best structure. If you check the formal charges and they're all 0, congratulations, you're right. That's the first thing you check. You want as many zeros as possible. The second thing, if you don't have all zeros, you must have some kind of charge. Fine. You want to make sure that the most electronegative atom has that negative charge. Okay, if you can help it. Sometimes you can't help it, well, that's too bad. But if you can help it, fix the structure so that the most electronegative atom would have the negative charge. Number 3 is, if you must have formal charges, then you want the difference between them to be as small as possible. If you have 1 and 0, -1, that's cool. If you have 3 and a 2, that's really bad. Okay, you want to get rid of the 3s and 2s, make them 1s at least, if not 0s. All right, talking about the rules, that's not really helpful. So let's actually look at some examples where we apply all of these rules, and then it will be more clear. We start off easy. Okay, ammonia is a really easy molecule to draw. A lot of you probably already know what the structure looks like, so you can just skip all of those steps. But I'm going to do this one step at a time, showing how this works. Okay, If you don't know how to draw this, following the steps will get you the answer all the time. So first of all, you have nitrogen and hydrogen. Who goes in the middle? It can't be hydrogen because hydrogen can never be in the middle. It can only make one bond, so it has to be nitrogen then. Once you decide that nitrogen is in the middle, you surround it with 3 hydrogens. Okay, notice the way I wrote the hydrogens down. It's not random. I made a triangle on purpose. Why did I make a triangle? Well, because you have to space them out as much as possible. You will connect the hydrogens with the nitrogen with a bond, and bonds are made up of electrons, and they're negative, and they're going to hit each other. So they want to be as far apart as they possibly can be. So 120 degrees for all of them is the most optimal distance, so you make a triangle. So once you do that, nitrogen has 5 valence electrons, hydrogen has 1, but then you have 3 hydrogens, so you multiply that by 3. You add them up, you have a total of 8 valence electrons for this structure. Okay, you count the total number of valence electrons. So next, you connect them with a bond. So the central atom has to connect with all the other atoms. You just draw a line, and each line represents 2 electrons because that's a covalent bond, right? So that means you used up 6 of those 8 electrons to connect the nitrogen to the hydrogens. What you should have left are 2 electrons. Okay, you just have 2 left, and then you will give those 2 electrons to whatever atom that still needs more electrons. In this case, the nitrogen. All of the hydrogens are satisfied. They have 2. That completes their octet, but nitrogen only has 6. Okay, cool, you can take them. So now nitrogen would have 8 valence electrons, and you subtract it from your total, you end up with 0 left. Okay, you always want to use up all of your electrons. You can't hold back. You have to use all of them. So once you use up all of your electrons, you go and look at your structure. Does that make sense? Does that structure make sense? Well, yes. Everything has a full octet. All right, but you're not finished yet. You need to change the geometry of your structure. You can't just leave it like that because now it wouldn't make sense. Like I said before, electrons are all negative, right? They all want to be as far apart from each other as they possibly can be. And right now, you've added 2 electrons to the nitrogen, and just because those 2 electrons are not in a bond doesn't mean they don't have a negative charge. They still have a negative charge, and they will repel the 2 bonds I just drew. Okay, I drew the 3 hydrogens in a triangle without the foresight that I will add 2 more electrons to the nitrogen. See, I didn't know I was going to add electrons to the nitrogen, so I just drew them in a triangle. But now I added 2 electrons. I must move those 2 bonds. So there will be a repulsive force that pushes those 2 bonds down to something like this. Now, ammonia, the proper Lewis structure for ammonia is T-shaped. All right, the 2 dots, the lone pairs, they also occupy space. So technically, they're all 90 degrees from each other, including the 2 lone pairs. And that is the proper way of drawing ammonia. So make sure you fix the geometry of the atom, because if you don't, that is inaccurate. And if you study polarity, you just might get it wrong. So checking full mole charges to see whether this is actually correct. Nitrogen has 5 valence electrons, minus the 2 lone pairs, minus the 3 bonds, you have 0. Good. Hydrogen always has 0. 1 minus 0 minus 1. You have 0 across the board. Congratulations. This is the correct structure for ammonia. Or does that make sense for everybody? I used all of the rules to draw a very simple structure just to show you that the rules work. Okay, anything to ask before we move on? All right, cool. The next example problem is a little bit more complicated. Well, because you have 2 carbons. Who goes in the middle? Carbon or hydrogen? Which one?
Carbon.
Carbon?
Well, obviously carbon, but which
Yeah.
carbon? Right, you have two of them.
Both.
Both, exactly. If you have two carbons, well, you have to be fair, they're both in the middle because both of those carbons need 4 bonds. And if you have 4 bonds, you're in the middle. So you will draw that like this. You draw the 2 carbons in the middle. You surround the 2 carbons with the 4 remaining hydrogens. And again, I spaced it out as far away as possible, okay? The way I did it, you will see later that all of the bond angles are 120 degrees so that they're not too close to each other. Once you do that, you start counting. Carbon has 4 valence electrons, and you have 2 of them. Hydrogen only has 1 valence electron. You have 4 of them. You do the math, you have 12 in total. And all of these atoms must be connected with each other, otherwise you're not in the same molecule, so you must connect them like that. How many electrons did you just use? 5 bonds, 2 electrons each, that's 10. So you consumed 10 electrons from your totals, and you would have 2 left. You need to put it back into the atom. Who needs that 2 electrons? Well, both carbons are dying for that electron. Well, you take a pick. I'm just going to give it that one because, you know, favoritism. So that carbon is now satisfied with 8 valence electrons. The other carbon, however, is crying in the club because it only has 6. So what do? What is the logical solution to this?
Add a bond.
Yes, socialism. You share. You see what I mean? Everybody has equal sharing. So you move that 2 electrons in, you have a double bond. And once you have a double bond, all of the carbons have 8. So everybody's happy. Everybody has a full octet. Does that make sense?
Yeah.
Of course, you can skip the step. You don't have to put the 2 electrons on one of the carbons. I'm doing that because I'm following every single rule. It's obvious that they have a double bond, but if it's not obvious, that's what you do. You put it, and then you decide, hey, I need a double bond.
So for these hydrogens, how do we know that it's diagonal and not like 90 degrees like the other one?
Oh, how do you know they're not 90 degrees? Well, you can try to make them 90 degrees, but if you do that, you're going to realize, wait, I have a big gap, right? If you imagine all the hydrogens being 90 degrees like the tabletop, if they're all perpendicular to the carbons, well, what about the sides? You have like a 180 degree between 2 hydrogens, whereas there's only a 90 degree between the hydrogen and the carbon. You see, you can do better than that, right? You have to be as far apart as you possibly can be.
Will the double bond be like more?
Technically, no. It's still all 120 degrees.
Yep.
All right, so do the formal charge to check. The 2 carbons are identical because they have the same bond. So 4 valence electron minus 0 non-bonding minus 4 bond, it's a 0. Good. Hydrogen always 0. So congratulations, this is the correct structure. Okay, you see, applying the rules always works. Okay, does that make sense, folks?
Yep.
Alrighty. Example 6 is different again. Okay, I will show you this one before I give you some practice questions. Cyanide is an ion. So first of all, you have a charge. And then this one doesn't really have a middle atom because you just have 2 things. And if you have 2 things, you can't say anybody's in the middle. So you just write them out, C and N. The convention is C goes before N. And let's count the electrons. Carbon has 4. Nitrogen has 5. And because this is an ion, you have a 1 minus. You have to account for that. You have 1 extra electron, so they add up to 10. And once you calculate that, you connect
2, 3, 4, 5.
I'm sorry? Was there a question?
No, sorry.
Okay. So you connect them using up 2 electrons. So 10 minus 2, you have 8 electrons left. Okay, now you need to put those 8 electrons into the molecule. Now you have a choice. Do you give it to the carbon or do you give it to the nitrogen? Right, so you have to make that decision because you have to give to the highest electronegative atom first. And if you have a periodic table, you can just check their electronegativities. Nitrogen has the electronegativity of 3. Carbon is 2.6, so nitrogen wins. Nitrogen calls dibs. So 8 electrons, right? So here we go, have two more, and there. Take 6 electrons. Nitrogen is very happy. Nitrogen has a full octet. You have 2 left. The carbon can have the leftovers. All right, so now you've used up all 8, and that's your structure so far. If you look at that structure, this is completely unfair. Nitrogen is completely happy. Carbon is starving for electrons. Like Bernie Sanders would have an aneurysm looking at this. All right, so you got to be fair. Socialism for the win. You give electrons from the nitrogen to the carbon, so you share them. You make a double bond. Is that enough?
No.
No, the carbon still needs 2 more. If you count, carbon has 6, nitrogen has 8. So you make a triple bond. So now both atoms would have 8 valence electrons. All right, so you are allowed to make a triple bond if that is necessary. What you cannot do is make a quadruple bond. You can't have 4 bonds with the same atom because the bond angles won't bend that way, but triple bonds are possible. So once you have the triple bond, you put it in square brackets, and because this is 1 minus, you put the negative charge on the top right corner. All right, now let's check the formal charges. Carbon has 4 valence electrons. 2 of them are not in a bond, and you have 3 bonds, that's a -1. Nitrogen has 5 valence electrons. 2 of them are not in a bond, 3 of them are bonds, so you have 0. The net charge is -1, so the formal charge must add up to -1. It does. Okay, in this case, the carbon has a -1. Now, I just said that nitrogen is more negative than the hydrogen, so really a better structure will have nitrogen with a -1, but there's no way you can do that. There's nothing you can do to fix that, so you have to be content with what you have. This is the correct structure for cyanide. Do we have any questions about that?
So you have to write the little -1 by the carbon.
Oh, you do not. I'm writing the little -1 to show you that this carbon has a -1, but realistically, I just want the structure. I don't care about the formal charges. It is a tool for you to check your answer. Okay? Does that make sense? All right, if I don't hear any other questions, attempt this one on your own. I will take it up in 2 minutes. All right, just follow the rules and you should get the answer. I'm going to pause the video. All right, so this is a fairly straightforward question. The first thing you have to figure out is who goes in the middle. And if you see a carbon, that's it, end of discussion. Carbon is in the middle, okay? If you check the electronegativities, carbon and sulfur, they're really similar. They have both 2.6. So you don't even have to decide. It has to be carbon because carbon can make more bonds than sulfur. So carbon in the middle, you surround carbon with the sulfur and the 2 fluorines. It doesn't really matter where you put the sulfur because you can just rotate the molecule and get a different version. So I just happened to put it on top. Now let's count. Carbon has 4. Sulfur has 6, fluorine has 7, and there's 2 of them, and they add up to 24 total electrons. And obviously, you got to connect them with a single bond, and you have 3 bonds, so 6 electrons were consumed, leaving you with 18. Now here, you got to make a decision. Who gets the electrons first? If you check the electronegativity, fluorine is number 1 on the periodic table with 4.0. It is the most electronegative atom, so okay, you get it first. You go 1, 2, 3, 4, 5, 6. And then you give it to the sulfur. Despite them being equal, you give it to the central atom last. So there, you just used up all 18 of your valence electrons. Carbon is not satisfied. Carbon has 6 valence electrons, so you got to make a double bond somehow. Which one do you pick? Okay, which one did you guys pick? Was it the sulfur or one of the fluorines?
Sulfur.
The sulfur, okay. Why did you pick sulfur?
Fluorine, you have to do both.
Fluorine has to be both?
Or like, if there's only one sulfur.
Oh, there's only one sulfur. I mean, I don't think that's the correct logic, but you're right, it's sulfur. It's just, it has nothing to do with how many of an atom you have. There are two reasons to pick sulfur over fluorine. One of them is formal charge. Okay, let me just choose sulfur first, and then I'll explain the formal charges. Okay, notice that when I made the double bond with the sulfur, I changed the electron location. Okay, I changed it because the sulfur has three things sticking out of it, the two lone pairs and the double bond, they must make 120-degree angles with each other. That's why I changed their locations. Make sure you do that too. So yeah, I suggest you do this with pencil so you can erase, then otherwise you have to write a new structure. So reason number one is formal charge. If you do that, well, carbon will have a formal charge of 0, because 4 minus 0 minus 4. The fluorines, they all have 7 valence electrons. 6 electrons are non-bonding, 1 bond, so that's a 0. And sulfur, if you do that, sulfur has 6 valence electrons, 4 non-bonding and 2 bond, you get full zeros across the board. That's why you choose sulfur. Okay? If you choose fluorine, you're going to end up with non-zero formal charges, and that will immediately tell you that it is wrong. You see what I'm talking about? So that's how formal charge can help you decide which bonds do I want to make. Because, if you don't know formal charges, it's just a guess. But with formal charges, it's not a guess. You know for sure. The second reason to choose sulfur over fluorine is electronegativity. Because fluorine has the highest electronegativity on the periodic table. It is really unwilling to share electrons. It wants electrons, so you're not taking my electrons. Sulfur has lower electronegativity, so it is more prone to sharing its electrons. So for that reason, it is easier to share electrons with sulfur than fluorine, because this fluorine is happy. It has 8 electrons already. There's no reason for that fluorine to give up electrons for the carbon. So you take it from the lower electronegativity. Okay, so 2 reasons. Make sure you take it from the sulfur. You can check with formal charge. If you took it from the fluorine, then you will quickly realize you're wrong if you do the formal charge, which is why we're learning formal charges. Okay, so do we have any questions regarding this question? So this is quite clear.
Yep.
The rules are clear. Follow the rules, and you will always get the right answers. Now, up to now, everything has been very normal. There are no exceptions to the rules. But in real life, some atoms can exhibit exceptions. Okay? Some Lewis diagrams, they don't have to satisfy the octet rule. They can have less than 8 electrons, and it's fine. How could this be? Well, 2 possibilities. Possibility number 1, if you have an odd number of electrons, then there's no way you can satisfy everybody. There will always be 1 single electron left behind, and somebody's not going to have 8. There's nothing you can do about that, so just do your best. The second possibility is, if you have boron and beryllium, those 2 atoms, they don't actually want 8. Boron wants 6, beryllium wants just 4, and they're happy with that. Okay, so if you ever have to make covalent bond with those 2, just know that you don't need 8. Okay, if you get 6 for boron, 4 for beryllium, you're good to go. And so those are the exceptions. So we're going to look at some examples of those exceptions. Question?
Why don't they want 8?
Oh, okay, that's a good question. Why don't they want 8? Well, everyone else wants 8, right? So what makes you special? Well, it has to do with their electron configuration. All right, so let me just draw the electron configuration for, I'll do bromine. No, sorry, I'll do boron. So for boron, I'm going to skip the 1s because that's useless. So you have 2s and the 2p's, right? Because boron has 2s2 and 2p1, it looks like that. Okay, does that make sense? We learned that last time.
Yeah.
To make covalent bonds, you need to fill up all the p orbitals to have a full 8. You see what I'm saying?
Mm-hmm.
I'm going ahead. This is tomorrow's class. But in order for anything to make a covalent bond, you have to promote this electron here. All right, so that electron is gone. So you have single electrons. And then they can go find a partner to bond with. And then you would have covalent bonding. But for boron, this electron can find a pair, no problem. This guy can find another electron, no problem. So you have 6 valence electrons. But how do you get 8? You need 2 more. Problem is that 2p orbital is empty. You can't make a bond with an empty orbital because you don't have an electron to offer. So boron is perfectly happy with just 6. It is unable to make 8. Does that make sense?
Okay.
Yeah, so that's quite a complicated answer, but that's the reason. And for beryllium, beryllium is just 2s2. That's beryllium. But if beryllium wants to make a covalent bond, you must promote the s to the p. And both of these single electrons will go out and find a partner. And you end up like that. You are unable to make more bonds because you just don't have any more electrons to find a pair with because your orbitals are empty. That's the reason.
Okay, thank you.
You're welcome. So you learned this in grade 12 because I know somebody's going to ask that question, why? And that's the answer. You can't explain this without orbitals. Okay, so Bohr diagrams are unable to explain something like that. So just keep in mind, boron and beryllium, they're special. Okay, aluminum is also special. Aluminum is satisfied with 6, but aluminum typically makes ionic bonds. Sometimes they make covalent bonds, but that is too much detail, so I wouldn't worry about that. Just remember these 2 exceptions. All right, so moving on to the next one, NO2. NO2 seems like a really innocent question. It's very similar to CO2, and CO2 is easy. A grade 10 student can tell me the structure of CO2. But NO2 is difficult because it is one of those exceptions. So let's try to do this. Nitrogen in the middle, because oxygen is more electronegative than nitrogen. Okay, I don't expect you to memorize these things. On the periodic table, you will see these information. And I draw them in a linear fashion because the 2 oxygen wants to be as far apart as they possibly can. So 180 degree and 180. All right, so nitrogen has 5. Oxygen's got 6, and there's 2 of them. They add up to 17. Uh-oh, 17 is odd. Somebody's going to be pissed. If you connect them, you use up 4 electrons for this, so you have 13 left. You give the 13 electrons to the oxygen first because they're more negative, so go ahead and take, well, you can only give them 12, and then you would have 1 left. You can give that 1 to the nitrogen because that's the only option you have now, so go ahead and take it. Well, this is your structure, and yeah, that looks ridiculous. The nitrogen has 5 valence electrons. That's really bad. The best thing you can do is give 2 more electrons to that nitrogen to make 7. If you can't get 8, the next best thing is 7. All right, so you try your best to get as close to 8 as possible. Which oxygen? Well, it doesn't really matter. I'm just going to pick one. So if you make a double bond here, again, I changed the configuration of the electrons on that oxygen, so that's 120 degrees for all of them. So now you have your structure. Okay, you can't satisfy nitrogen too bad. Also, that single electron is still negative. That means it has a repulsive force. It will push the 2 bonds down. It wouldn't be 180 straight line anymore. So you will angle this. And this is the correct structure. If you do the formal charge, very sad, the nitrogen has a +1. All right, 5 valence, minus 1 lone electron, minus the 3 bonds, you have +1. The single bond oxygen, 6 valence electrons, minus 6 non-bonding electrons, minus 1 bond, that's -1. And the double bond oxygen is very happy with 6 minus 4 minus 2, that's a 0. So in this question, you don't have zeros across the board. But that's the best you can do. There's nothing you can do to rectify that. All right, you're going to have a 1 and a -1. but that's okay because that's the next best thing to full zeros. All right, does that make sense, guys? So any questions about that?
Why don't you put a double bond with the other oxygen? Would it
Okay,
not
good question. Now, if you put a double bond with that oxygen, you solve the formal charge problem. Everybody will have a formal charge of 0.
Yeah.
But you cannot do that because if you do, nitrogen will have 9 electrons in the valence shell, and there isn't enough orbitals to contain 9 electrons. The maximum is 8. You cannot exceed 8, so you have to stick with 7. Does that make sense?
Yeah, it does. Okay.
All right, so like, does it matter which oxygen I take the electrons from?
No.
No, I chose the one on the right because I had to make a decision and there was no reason for that. I just wanted to do that one. You could, of course, take it from the one on the left. And in fact, this happens. This is something called resonance structure. Okay? This particular molecule, it has more than one possible answer. If you give me any of these two solutions, you will be marked correct. In fact, they oscillate between each other. The molecule literally switches between the two orientations pretty much all the time. What happens is that electron pair from the single bond oxygen will be shared between the nitrogen and the oxygen, and this will break the double bond on the other side, returning those electrons to that oxygen. You will get the other configuration. And later, this will revert back, and it will go back and forth, back and forth. This is resonance. To represent resonance structure, you can use the bottom structure. Instead of drawing solid lines, you use dotted lines. If you have a dotted line, this is telling you that this has the potential to be a double bond. The condition is the other bond must be a single bond, and vice versa. Okay, each oxygen will then have 6 valence electrons. What happened to the other ones? Well, they're the dashed lines. So a resonance structure of NO2 looks something like that. And you have to know what that means. That means that the dashed line could be double or single. Okay, if one of them is double, the other one must be single. And if you're single, the other one is thus double. Okay, so you have to know how to draw resonance structures if resonance structures exist. Okay, are we clear about that? All of these structures are equally correct. They're all acceptable. You good? All right, so let's move on to BH3. BH3 just has boron and hydrogen, so obviously boron is in the middle. Hydrogen was never in the middle. Boron's got 3 valence electrons. Hydrogen has 1, and you have 3 hydrogens. You have a total of 6. You connect them. Oh, look, I just used up all 6. That's it. You don't have any more electrons to give. Boron, you have 6. Hydrogen, well, you have 2. You do the formal charge. Boron has 3 valence electrons, no non-bonding electrons, and 3 bonds, 0. Good. Hydrogen, always 0. So you can see that BH3 is perfectly stable. All right? They're perfectly happy, zeros across the board. That is your final structure. Okay? That may look weird to some people because you don't have 8, but that's just boron. All right? And the last example for this lesson, beryllium dichloride. Well, beryllium has to be in the middle because chlorine has really high electronegativity. Beryllium has 2. Chlorines, they have 7 times 2, 14, plus 2, 16. You connect them, so you have -4 and 12 left. By the way, this has to be a straight line for the same reason. Okay. Again, you want to be as far apart as possible. So you have 12 electrons remaining. You will give the chlorines 6 each. And once you do that, you will have run out of electrons. You would have 0 left. You have nothing for the beryllium, and that's fine. Do the formal charge. Beryllium has 2 valence electrons, no non-bonding electrons, and 2 bonds, 0. Chlorine, 7 minus 6 minus 1. Again, you have 0. All right, so this is a perfectly stable structure. Any questions about that? So far we've learned the basics of Lewis structures. We learned how to use formal charge to determine whether a structure is correct. And we learned few exceptions of the octet rule. Sometimes you don't get 8. Okay? So this is it for this lesson. All right, we're going to take a short break, and then we're going to move on to the next lesson, which is more liquid structures, and that lesson will be a lot harder. It will be based on the knowledge from this one. Okay, so any questions before we end this? All right, good.